All right, ladies and gentlemen, welcome to the next episode. As we promised, we're back. We're back with Arthur. Double Arthurs are here. And today we are going to be discussing a very, very interesting topic of Apple Vision Pro lens stack. So those two bad boys will be discussing in-depth technical analysis of how those lenses are built. I will be the moderator. The expert is here, and welcome, Arthur. Thank you for coming back to our channel.
Hello, guys. Thank you for inviting me.
It's my biggest pleasure. So I guess without further ado, we can dive into the optical stack of Apple Vision Pro because it's an amazing device and it definitely deserves a deep dive. So the floor is yours. And I'll be asking questions alongside.
Okay, let's share the screen. Now I will be using some materials. First of all, when Apple Vision Pro was released, they published this article about our estimations about Apple Vision Pro, and we will compare the estimations with what we have in actual. And we will use a lot the articles by Karl Gutak here, and some measurements that were made by Brad about field of view. And I fixed it teardown of Apple Vision Pro. So I prepared slides, and let's go according to slides.
All right, let's do it.
So just a moment, my colleague Shimon Gvarnik helped me with preparation of this material. He did ray tracing of Apple Vision Pro lens, and I will present that as well. So in June 23, we just had pictures, so we tried to estimate the field of view by means of lenses size, and today we have actual values. We were very close for that, and now we also have this lens stack as one unit, so it was easier for us to model the lens stack. Now we also have a display removed from the stack. We know the size of display, and what is most interesting is this 6 degrees angle. So each visual unit is tilted one toward each other by 6 degrees. This is to increase temporal field of view and common horizontal field of view. So that was also our estimation in June 23. We estimated 5 degrees of this tilt angle, and we also estimated a total field of view that was overestimated. Now it was measured by Brad, 112 over 80 degrees, and we estimated 120 over 85. So it was visual scenario.
Some people might be getting it, right? Depending on their shape of the face. No, you don't think so?
Okay. Still not.
Okay.
Now, that's what we had in June, the picture of lens stack, and we were breaking our head to understand the architecture. So I did some research and find out that it's actually not 3 lenses, but 2 lenses. And the first lens is separated to 2 parts by a cylindric surface. And that because of very important component named quantum wave plate or retarder. You see here quantum wave plate or retarder that cannot be stretched, but it could be folded cylindrically. So yes, it was also validated by patent of Apple. So having this model and knowing approximately directions of this, the dimensions of this model of Apple, we modeled the lens. And as you can see, there are two lenses, not three, but the big lens is separated by cylindrical surface. If we look from top, we see arc, and if we look from side, we see direct line. Now we estimated in the model, we estimated different dimensions. We took 12 millimeters eye relief. Total stack is 13 millimeters, but we have extra because of concave shape of the lens. Now here we have ray tracing for peripheral vision. When eye is looking straight, I can perceive most of field of view. Another simulation is for rotation of the eye. When eye is looking straight and getting stimulation in peripheral vision, eye wants to rotate. We want to rotate our eyes to the place of stimulation. Like here, you see the pupil now is in new position. And so rotational visual simulation is different from peripheral. And usually it's right to make optimization of the lens for rotational gaze, not for peripheral. Now, next we did modeling.
Just one question on behalf of our users. I know many users will be asking this question. Apple Vision Pro lenses are unusual for naked eye, are unusual because they have a different shape. So they're not going out of the lens, but they're going into inner circle. That's what's unusual for many people when they see this for the first time. Can you, in one sentence, explain why Apple did it?
Why the shape is oval and not round?
Not oval. No, it's not oval, but it's going into inside of the into the inner part of the shape.
Why it's concave?
No, why not protruding outside? Yes.
Why it's concave? It's
concave,
okay.
Correct.
Okay. So very important parameter is eye relief. We need to position lenses some distance from our eyes because of eyebrows, and to have a convenient distance. So 12 millimeters is fine. Less, maybe 10 millimeters still okay, but less makes us uncomfortable. And now this is geometry. This is school geometry, how much field of view you can get, because the rays should enter into the pupil of the eye. So if you have flat lens or convex lens, the peripheral zone of the lens has more distance from the eye. So if you want to get more field of view, you need to enlarge diameter of the lens. But there are constraints on the diameter of the lens, especially when we use micro displays that's very small, so we cannot make big lenses.
Yeah, 1.4 inches. Yeah.
So concave shape of the lens helps us, despite of small diameter of the lens, to get a lot of field of view. This is the
all right.
main reason.
Thank you.
Now, what else I can mention here? You can see that peripheral vision is bigger, has bigger field of view than rotational. The issue is that with peripheral vision, we need to direct rays into pupil, and with rotational into center of eye rotation. And because of the same lens surface, and its diameter of the lens is limited, the rotational vision is ended by about 40 degrees field of view, while peripheral can have something around 50 degrees field of view. So when we talk about field of view, we usually talk about peripheral because it's bigger. But we need to know that there is also rotational field of view. Now,
all right.
Let's. I will show you the model of the lens from a different perspective, from side view, from top view. So this is the side view and side top view of the lens. Next, here is explode view. I will explain. Yeah, I can explain right now. The green one, what you see here is a quarter wave plate retarder, and the red one is a reflective polarizer. Two elements required for pancake lens. Now, if you look from top and make explode view, so we took this first A lens, then we took a retarder, but when we look from top, it's not like when we look from side, it looks like that, this retarder. Then second part of first lens, and this is reflective polarizer that could be laminated over a spheric surface. But retarder, the green one, cannot be laminated over a spheric surface, and that's why the first lens is divided by it on two parts with cylindric cut. So now we bring this picture that Apple published with those three lenses, and we compare with the model that we simulated, so to see how precise the model is. So we can see that lens 1B in our case is a little bit smaller than in real case, and lens 2 is a little bit bigger, but we will get approximately same results, not optimized, of course. What I will going to show you was the result of 2 hours of work. I guess Apple worked 100, maybe thousands of hours on optimizations, but the principles stay the same. So again, those red surfaces are not lenses. Those are this surface is thin film reflective polarizer, and this surface is thin film retarder, water wave plate. And now to make analysis, we took into account the real resolution and the size of the pixel used in microdisplay. So we did ray tracing. We ran optimization only for 2 hours, and as I said, the thickness of the division between lenses is a little bit different from the real model, but I will present your results of this modeling. So one of the most important parameters is the RMS spot size in microns versus the view angle. And what you see here...
Could you explain to people what the RMS stands for?
Root mean square. That is meaning if we making reverse backtracing, the rays that coming out from the eye are collimated, like parallel rays, like we see in reality, and they hit the display. They hit display despite that the rays are coming in a bundle of 4 millimeter diameters, like our eye pupil. They are not hitting, they are not focused exactly in the one point all on the display, but they have spot, some spread spot. And this spread spot is measured by a root mean square, something like Gaussian distribution of rays around the focus, and it's measured in microns, the same like pixels are measured in microns. And if you take one pixel of 7.5 microns, we see that the RMS could follow one pixel up to 24 degrees, and then it's rising up. And from our experience, we know that until 2 pixels RMS, you can expect a sharp vision user experience. And now, interesting thing, considering this tilting of visual unit by 6 degrees,
Mm-hmm.
If we want to estimate sharp vision angle, so it's in addition to 36 degrees, we adding this 6 degrees for temporal view, so we can expect 42 degrees sharp vision when we look in temporally with the eye. And nasally, we need to subtract, so we get 30 degrees. But it's enough because vision physiology is built like when we're looking into with the eye into nasal direction. After 30 degrees, it's outside the comfort zone for nasal direction view.
But
And,
just for the correct interpretation of these conclusions with the degrees you're saying here, so what is the sharp field of view people see in Vision Pro overall? Is that 84 or is it less? What is your kind of estimation there?
So we mostly are looking straight, or there is you may know the eyes are scanning the picture all the time. It's called nystagmus, but we are mostly looking straight and rotating our eyes in comfort zone, usually up to 30 degrees. Sometimes we look in more than 70 degrees, but up to about 25 degrees, it should be perfectly sharp. Now, as I said, this is only first approximation. It's not exact modeling of the lenses.
Sure.
I'm sure that they are better than on this graph. And probably till 40 degrees, you will get those curvatures as 1 pixel. So my estimation, I didn't look into Apple Vision Pro, but my estimation that it's sharper, that it's better than you see here. We can look on the pictures of Carl Gutak.
And when you say, sorry, just one more question for the viewers. When you say it's perfect, but when it becomes less perfect, when the chart is going off, what kind of artifacts are you expecting people to see from the moment when it's not perfect? Could you describe them just briefly?
It will be less sharp, but up to 2 pixels. You probably wouldn't notice that unless you have specific test targets. And as you know, Apple did a work that find it to, for instance, letters with small fonts to increase them. So there will be no too fine details. So to get a sharp perception in any case.
Yeah, I can tell you from my experience, the sweet spot is very good. So you can see sharp very well because also they're optimized the software in a way that the letters are always in the right distance with the right size from where you look. So that's one thing. I obviously see, if I look, not many people do that, but if I look really like this on the sides, I start seeing some color shiftings and some other, image swimming, let's call it like this. But yeah, the sweet spot is I would say fantastic. It's really good.
Yeah, let's talk about pixel per degree. According to our model, it's in the middle. It's 44, and it's reduced till something like 39, and it's matching the analysis done by Carl Gutak. Now, when you spoke about sweet spot, it's what will happen if you provide your headset personalized for your face to your colleagues? Did you have complaints that it's not sharp enough?
Yeah, it won't allow you. Automatically, when someone takes it on their face, it measures and adjusts their IPD and calibrates the eye tracking. You cannot use on different person setting. It's always on their own perfect setting for that person.
Yeah, maybe the reason we did analysis for different pupil shift of ±2 and ±4 millimeters, so we can see that for the cases of +2 millimeters, the sharpness is going down quite fast after 20 degrees view angle, and for 4 millimeters, it's immediately not sharp. That is why IPD personalization is very important.
And I think that is why here I can give you a so first of all, Apple Vision Pro personalize every IPD for every person separately, but on top of that, they move each lens separately. So it's not moving at the same time, but separately. I can tell from our perspective at Somnium, we actually wanted to do the separate movement of two lenses. So we wanted to do two IPD adjustments. But after testing, because of quite a huge sweet spot on our side and the size of the lenses, we decided that it doesn't bring that amount of benefit to actually have the second part and make the mechanism much more complicated. And our testing with users and also with YouTubers kind of confirmed us that you can actually go ±4, 6 degrees of IPD adjustment, millimeters of IPD adjustment, and kind of still feel in the sweet spot. But I can understand why Apple is doing it because they're operating in different margins.
I mean millimeters, not degrees.
Yes.
Okay.
The millimeter, yeah, I said millimeters, and the Apple has tighter sizes and margins to operate with. So definitely understandable why they do it.
Yeah, so in your case, when you have bigger eye box, there is no need to make separate pupillary distance adjustment for each eye, but it's known also from optometry that pupillary distance could be different for each eye, but not too much different.
Yep.
In the case of Apple, since the eye box is very small, maybe it's critical to make separate PD.
I'm sure it is. I'm sure it is. Yeah.
Okay. Let's see what else. Pupil swim. This is simulation of not a precise model, but it shows that there is a pupil swim. The meaning, when we look to periphery, when we look straight and feel something on periphery and will rotate our eyes to corresponding pixels, we will miss. How much we will miss? It's, for instance, here on 35 degrees, we will miss about 13 pixels. So I guess there is a pupil swim also in precise lens modeling, but once we have real-time eye tracker and can fix distortions in real time, pupil swim is eliminated. Now about Vergence accommodation challenge.
Oh, yes. I can confirm that this is one of the things which I had my own review of Vision Pro, and this video will come after that review. And I love the device. It's amazing. But one thing which pass-through kind of felt that it could improve it for me is that it is very hard for me to sharpen my view on the mobile phone. Even if I put it further away from the device, it's better, but still it's very hard to read through and to kind of focus on those. So I think that will explain why exactly this is happening.
So to explain that our visual physiology is different from one to another, but there is, what is it, Vergence accommodation conflict. There is also Vergence accommodation correspondence measured in diopters. So when the object is coming closer to us and we're looking on it, let's say with one eye, we're doing accommodation to keep it focused on the retina, and Vergence is when we're looking with both eyes to keep fixation on the object, so the object will fall on the fovea of the both eyes. Now, this Vergence and accommodation intraocular lens changing the focus, they have correspondence in real life. And in virtual reality today, there is no possibility to stimulate accommodation. So everything above one diopter maybe less than 1 diopter, should make us feel uncomfortable. And when it's more than 2 diopters, our brain is taking decision to make vergence or to make accommodation. So when you look on your smartphone, that you bring it very close to your eyes, like 25 centimeters, it's 4 diopters of should be 4 diopters of vergence and accommodation. So from vergence perspective, it's 4 diopters. But from accommodation perspective, it depends where there is accommodation plane of Apple. But let's assume 1 meter from our eyes, so it's 1 diopter. So there is a difference of 3 diopters, and your brain is taking decision to make vergence and to apply accommodation, so you will see blurry, or you should close one eye.
That's exactly what I do. I either close my eye or just take it off and read the message quickly. But you're right. That's exactly what's happening.
Yes. Okay. So this challenge Apple should resolve like any other VR and MR company. By the way, in Hypervision, we are starting to work on this solution with another European partner. What else? Let's compare Apple Vision Pro Optics versus Meta Quest Pro and Pico 4. So on the left side, you see architectures of based on fast LCDs, and Meta has 2 lenses, and Pico has 1 lens. But what is common for those 2 cases? The lamination of thin films, doing manipulation to polarization, are done on flat surfaces. Once it's done on flat surfaces, you see it's like that. You have here cleaner polarizer, then reflective polarizer and water wave plate, and a lot of substrates in between. So it's this thin films create thick film stack. Now the disadvantage of that, when you have to make flat surface, you cannot optimize optical performance here. But it's standard process, so the costs are not so high. In opposite to that, Apple did a big leap. So as I explained before, there is a quarter wave plate embedded between 2 cylindrical surfaces, and reflective and cleaning polarizer, maybe cleaning, I don't know, but we think that there is a cleaning polarizer, is on the aspheric surface. As you can see here, it's not easy process, not cheap process. You need to stretch flat thin film over aspheric surface. There is a yield in this process, but Apple did that, and all respect for the vendor of Apple who did manufacturing for it. I think it's GCO, Taiwanese company, if we assume correctly. And the big respect for this company. As a result, you can allow much better optical design because all surfaces are carved. But again, you need here in this implementation 1 extra lens. And this 1 extra lens adds complexity, of course, and costs. Do you have any questions about this slide?
I think about this slide is quite clear. For me, I think one question, I'm not sure whether you will touch upon that later, but I think it's a good slide to discuss it. If I talk about optical performance of Vision Pro, I think it's great. One complaint I personally have, and many people also notice that, is that there's a lot of reflections and glare in a bright scenes, which are happening when you have a dark background and a bright scene on the movie or somewhere. There's a lot of reflections happening. Could you explain to the viewers briefly why this is happening and how could Apple and other manufacturers actually solve that problem in the future?
So those ghosting images are created typically in pancake lens modules because of multiple reflections from the surfaces before the rays are coming out of the lens into our eyes. Through those multiple reflections, some unwanted light is passing instead of reflections, is passing through the lenses and creates ghosting images. In some cases, there are undesired reflections, and then those images are passing. From our simulations of ghosting images, there are more than a dozen types of ghosting images in pancake lenses, and it's very important to the manufacturer to make technology of retarders, meaning quarter wave plates, polarizers, reflective polarizers, and in addition, anti-reflection coatings or half mirror coatings in such way that every surface will work as intended, without undesired reflections and without undesired transmissions. And today there is too much undesired reflections and transmissions. This is making ghosting images. This is reducing dynamic range. Even with very bright displays, you cannot make a high dynamic range because you raising brightness of the display. You also raising brightness of the ghosting images. So you're making a shifting of the black level in this case. Okay.
Yep. Yeah. I mean, I agree with that.
I suggest in another session that we will record, we will talk about pancake lens architecture in more deeply, and we'll discuss those ghosting images, how they created, and
I'm pretty sure people will agree with us and with me if I say yes, absolutely. We should dive deeper in our next session about the pancake lens architecture. For example, not in advertising, but for example, in aspheric lenses, the glare or the ghosting is close to non-existent. It's a pleasure to see in the dark, contrast scenes that you almost don't have no ghosting at all. But obviously the downside is the size and everything else. But
by the way, in Somnium VR1, each visual engine has two lenses in stack, right? Now, yes. The question to you: are you making anti-reflective coatings or
yes.
lenses?
Yes. Yes.
Now, there are two types of anti-reflective coatings. The one that is used in prescription glasses, that 4% of reflection reduces to about 1%. And the second type is the electric one that could reduce it to 0.2 to 0.1%. The question: what type of coatings are you doing in your lenses?
That question I need to ask our engineer, but I can tell you that when measuring I think the first type would be the right answer, because when measuring the differences between coated lens and uncoated lens, the difference is marginal. Let me say like this, right? Because already, even without the coating, there's close to no glare at all in a very contrast scenes. If you have a black background, white text, and things like that, but with the coating, the difference is there, but it's minimal. So, but I could ask, and we could discuss that in the next episode.
So if we talked about coatings, now this is the last slide, and it explains current Apple Vision Pro lens model and Wishful. So if we're talking about coatings, you see this green dashed line. This is 50 dielectric mirror coating. So of course, in your case, in Somnium VR1, no need for this coating. Now, what we have over display is another quarter wave plate that, together with quarter wave plate, that inside the lens you see dashed line and continuous line. It depends, we looking from top or from side. This is another quarter wave plate. And then we see a reflective polarizer and cleanup polarizer here. So this is current implementation of the Apple Visual Pro visual engine. Now the challenge is to make water wave plate, reflective polarizer, and cleaner polarizer all into one single stack applied over a spheric surface, as you can see here. You see there, in this case, we don't need such thick lens. It could be much thinner lens, thinner optical module, less weight, and less cost, of course. But to make this lamination or integration of 3 types of thin films over a spheric surface like that, this is a great challenge. And I believe that in few years this challenge will be resolved, including we are in Hypervision just started a project with American company doing liquid crystals for optical polarization coatings. So we are doing project to make such coatings over carved surfaces. Such coatings over carved surfaces that probably we will resolve this challenge, maybe others as well. So estimation that it will take about 2 years to get lenses like you see here on the right of the picture.
So, okay, that's an interesting point because all the leaks and information out there are saying that Apple will introduce the next generation of the Vision Pro and maybe something else, maybe Vision Lite or Vision, in 2025, September 2025. So in the end of 2025, with real shipments probably closer to Christmas, right? So do you think that this could have a chance to be in those headsets, or it will still be the older optical stack? Because I think they will need to stay with the same screens, meaning that it will be still 1.4 something inch screens, but so the size will not go up. So they will have to dance around the optical stack. So what are your thoughts about that? Because I myself and a lot of people think that next gen Vision Pro 2 and other headsets will be coming in 2025 in the end.
Okay, so answer will be maybe a little complex, but Apple is never in rush. So we were waiting for Apple Vision Pro maybe 4-5 years.
5 years, yeah.
And it was starting not for pancake lens. As I remember, there were rumors about multiple Fresnel lenses, if you remember. So also in this case, when Apple says that at the end of 2025, there is a big
they
chance.
say nothing. They say nothing. Analysts are saying this, not Apple. Apple is quiet.
Okay. Still, it could take a few years more.
Okay.
Now, next point. About 2 years ago, Apple acquired Limbach.
Producer of the lenses for Lynx.
Yes, and Limbach has a very creative, great guys with 10 years of experience in designing optics for virtual reality, and I guess they prepare something interesting.
Yeah, Limbach guys, if you're watching, put some comments below. Say hi to us.
So probably this will be something in between what we have now and what I show you here. It could be some surprise because every time they bring some surprise, and I have to say a lot of my inventions were inspired by Limbach's design.
Nice.
And my colleague Shimon. So we can expect surprise from Apple.
Okay. I certainly hope so. I mean, as I said, to me, this device visually I would love to have better field of view. That's one thing where I can feel that their improvement is needed because you can still feel the constraint a little bit. It's not disturbing, but it's something which I would love to improve. And probably ghosting. If they can improve those two things marginally, that will already be a big update because other than that, the visual stack of this device is very good. It's pleasure to look through it. It's a very good image. It's good quality. I think in VR mode, it's a good brightness. In pass-through mode, brightness could be better. But generally speaking, it's a good optical stack. So congratulations to Apple for doing a good job on that.
One more thought about Apple Vision Lite, not Pro. It should be with very reduced costs. So I hope that Limbach engineers in Madrid today, or maybe also in the United States, are working on another option of lenses to work with fast LCDs and not with micro OLEDs. And
Interesting.
why I hope that this will happen? Because fast LCD manufacturers are awaiting for big order in order to release 4K fast LCDs. Because today the biggest
How many inches?
resolution,
What is the size of the fast LCD for 4K?
2.56 inch. This looks like
Okay.
the standard size of
Yep.
the fast LCD, and today we have 2.16K resolution and also 2.7K resolution, but 3.84K resolution was demonstrated last year on Display Week by Innolux, but never we never had plans about to put them into mass production. So in the case that Apple will make light version with reduced costs, they probably will stimulate the fast LCD manufacturers to release 4K fast LCD.
Fast
And
LCDs are not dead. Just for those fans of fast LCDs, who I am as well part of that group.
and there
But
are a lot of advantages if to work with fast LCDs, like iBox, like very big iBox. Two main advantages, yes, and the cost, of course.
yeah. Okay. I think with that, we're all looking forward. First of all, thank you for this in-depth analysis. I, as always, learned a lot. That's why I love to do those in the first place. But we're all waiting for what Apple will bring to the table in the next generation of the headsets. I'm also waiting but not only waiting, but cannot wait for some more improvements and some other surprises from you, Hypervision guys, in terms of the design of the lenses and what we will bring together to the next generation of VR1 headsets and other headsets with whom we are working as the conglomerate of companies and group of companies, and probably even other partners. Yeah, it's an exciting time. Finally, there's more players and player like Apple pushing forward this industry together, and I think it will just bring a lot of benefit to everyone. With that, I thank everyone who are watching. Don't forget to maybe comment on this video. What do you think about next Apple headset? What would you wish to have in the next in the next optical stacks? Where would you want to have improvements? And until the next time, as we will discuss the pancake architecture and maybe compare them to different types of architectures and see what the future holds. So thank you, Artur, and thank you, everybody. See you
Thank you,
in the next
always
episode.
pleasure. Thank you.
Bye bye.